Welcome to Hi-Fi, a high-yield physics lecture series to help you become a better radiation oncologist and help you pass boards. This video will be reviewing factors that influence dose calculations. Say you need to treat a patient emergently over the weekend. You will need to perform a hand calculation to determine how many monitor units, or MUs, you need to deliver your prescribed dose. First off, what exactly is a monitor unit? Well, one monitor unit equals 1 centigrade under very specific or reference conditions. Let's assume that your clinic uses the typical reference conditions and defines a monitor unit to be 1 centigrade delivered along the central axis of a 10 by 10 centimeter field with a 100 centimeter SSD at the depth of maximum dose, which we call Dmax. When we prescribe a particular dose in centigrade, it is ultimately delivered by the LINAC in monitor units. Remember, the monitor unit is defined at reference conditions, but these conditions are not typically the case for our patients. As we change these conditions, the number of monitor units required to deliver a particular dose also changes. Let's think in generalities about how and which factors will affect our dose calculation. These include depth of treatment, beam energy, distance from the source, and field size. Let's start with the patient and the depth of the target. The separation or thickness of the patient is going to affect how many monitor units are required. As the photons pass through the patient, they will be attenuated by the tissue. The wider the separation or the greater depth you are treating to, the more monitor units will be required. The next factor to consider is beam energy, which can range from 6 to 18 megavoltage in most LINACs. Since generated photons are a result of Bremsstrahlung interactions, they have a spectrum of energies. Specific to each energy is a maximum energy, a mean energy, and a Dmax. For example, a 6 megavoltage beam has a maximum energy of 6 MV and a mean energy of 2 MV, because mean energy is typically about 1/3 the max, and a Dmax of 1.5 centimeters. As photons interact with tissue, they are attenuated and dose builds up, as we showed in these curves. Why does it happen? The photon-tissue interaction generates electrons within the tissue, which deposit the dose. Let's compare 6 and 18 megavoltage beams. Think of the photons like two football players, with the wimpier or lower energy photons getting stopped by what they encounter, whereas the stronger, higher energy photons are not. But what does energy do to our monitor unit calculation? Because the lower energy photons are stopped easier, their Dmax is shallower, and you need more monitor units to make sure there are adequate photons at play to deliver ionization or dose where you need it. The next factor to consider is SSD, or source to surface distance. This refers to how far the source of the radiation is from the skin surface of the patient. Why does this matter? Doesn't the beam interact similarly along the whole path whenever it encounters the patient? No. The beam is diverging, so its intensity will decrease as we move away from the source. Think of the photons as runners starting a race. Everyone is clustered together, but as you leave the starting line, everyone starts to spread out. Imagine using the collimator to shape a 10 by 10 centimeter squared field at the surface of the patient. Now, if you move the patient twice as far away, this field will now be 20 by 20 centimeters squared. So the area of the field has grown from 100 centimeters squared to 400 centimeters squared, but you still have the same number of photons. Therefore, the intensity, or the number of photons per unit area, has decreased by a factor of 4, while the distance increased by a factor of 2. This is known as the inverse square law. The intensity is inversely related to the square of the change in distance. So as SSD increases, the number of MUs needed will also increase in order to make sure more of your downstream runner photons are available to interact with your target. When we set the isocenter, or center of rotational axis, on the patient's surface, that is what we refer to as an SSD setup. When we say set up SSD style, we usually mean at 100 centimeters. Now keep in mind, even though the isocenter is at surface for this setup, you prescribe and treat to a depth beyond the isocenter, so inverse square will need to factor in. In this circumstance, we use percentage depth dose, or PDD, for our MU calculations. What is PDD? PDD equals the ratio of the dose at a given point, or depth, in a phantom to the depth of maximum dose, Dmax. These values are calculated by physicists for each machine and beam energy, which can be found in your clinic's lookup tables. An MU calculation with SSD setup uses PDD. This PDD curve illustrates how PDDs build up initially as the depth approaches Dmax, and then begin to decrease as the photons move deeper and deeper in the patient. PDDs, quote, fall off with depth both because of inverse square law and photon attenuation. Now that we understand SSD, the inverse square concept, and PDD, we need to understand the more common scenario of an SAD, aka isocentric, setup, and TMR, or tissue maximum ratio. When treating a patient with more than a single beam, it makes sense to put the isocenter inside the patient. This allows the therapist to rotate the gantry and deliver multiple beams without moving the patient. In this situation, the patient is said to be treated with a source-to-axis distance, or SAD technique, also referred to as an isocentric technique. With SAD setups, the SAD is held constant at 100 centimeters, and MU calculations are performed using tissue maximum ratio, or TMR, rather than the PDD. TMR is the ratio of the dose at a given point, or depth, in a phantom to the depth of maximum dose, Dmax. These values are calculated by physicists for each machine and beam energy, which can be found in your clinic's lookup tables. Sounds familiar, right? Up until this point, it is exactly the same as PDD. But here's the deal. TMR is PDD with the distance from the source to the point of measurement held constant. So inverse square does not come into play here. So in TMR, the photon attenuation is from the interaction with tissue only, whereas in PDD, photon attenuation is from the interaction with both tissue and the inverse square component. Because the point of measurement is fixed at isocenter in SAD setups and does not change, TMR is used in MU calculations for SAD setups. This brings us to our last factor, field size. Output changes with field size. Intuitively, larger field sizes allow more photons through, and vice versa. Therefore, the number of monitor units required depends on field size. When photons are generated, they proceed to the patient as either primary or scatter photons. The dose distributed at the calculation point results from both these primary and scatter contributions. The primary contribution refers to photons directly reaching the calculation point along the beam path. Scatter contribution is from photons that interact with something and scatter toward the calculation point. The general term scatter encompasses both collimator scatter, or S sub C, and phantom scatter, S sub P. Collimator scatter, or S sub C, refers to photons that scatter to the calculation point after interacting with the collimator or machine components in the head of the linac. The larger the collimator surface area exposed, think increasing field size, the greater opportunity for photons to be scattered. Phantom scatter, or S sub P, refers to the photons that scatter to the calculation point after interacting with patient tissue. The larger the region of the patient exposed to radiation, again, think field size, the greater volume for photons to scatter. Increasing field size increases both collimator and phantom scatter factors, the product of which is commonly termed output factor. Since reference conditions are for a 10 by 10 centimeter field, we have to make adjustments for output factor when using larger or smaller field sizes. For fields smaller than 10 by 10, there will be less scatter and more MUs required. For larger field sizes, there will be more scatter and less MUs required. But what if you don't have a square field? This requires the calculation of an equivalent square field size. Since the collimator jaws define a rectangular shape, we can calculate the field size as 4 times the area, all divided by the perimeter. For example, if a field measures 5 by 10 centimeters, the area is equal to 5 times 10, which is 50, and 4 times 50 equals 200. Then we divide all of this by the perimeter of 30. This gives us an equivalent square field size of 6.7 centimeters. This value can then be used when setting up our MU calculation. Okay, let's recap. We learned how target depth and patient thickness, SSD, field size, and beam energy affect the MUs needed to treat a patient, and the difference between PDD and TMR. We will apply these concepts with calculations using clinical scenarios in our next video.